So last lecture, I started to talk about mutual inductance between two wires. So they are not connected together, and there is current on the loop one, and if the current is changing, and we know that it will create the magnetic field, and the magnetic flux, for the loop two will changes. So once they are changing the magnetic flux, and we know that there will be current that are flowing through. This is a loop, the second loop, and here you see that even though there are no direct connections between the two wires, so if we change the current I1 in the first loop, there will be current flowing in the second loop. And then we also talk about that, the I1, of course, the loop will also create this magnetic field. And once it is changing, it also changes the magnetic flux, for the first loop for itself. And we know that if it changes itself, that also create the current. Okay, that is equivalent to the electromotive force. And we also, said that according to Lenz's law, that this induced EMF is in such a direction as to oppose any change in current. Okay, for this reason, it is also called a back EMF. Okay, so we can think about that the work done against this the back EMF. When we turning on a current, we can calculate that, and we will regard it as energy stored in the magnetic field. Okay, so then we can calculate the energy in magnetic fields. Okay, the way to do that, we can first think about the work done on a unit charge. Okay, so the work done on a unit charge against this back EMF that I discussed earlier. Okay, so if we do it in one trip, around the circuit, that is really minus epsilon. Okay, here this minus sign really indicates this is the work that we have to do against the back EMF in order to get the current going. Okay, so we know that we know this is really equals to epsilon is really minus d phi over dt is really the rate of change for this magnetic flux, and this one is really d phi over dt. Okay, and phi we said can be really di over dt. Phi is really the self-inductance, times the energy. Okay, so this is what we have. Okay, so once we have this, and we also know the amount of charge per unit time passing down this wire is really the current I. So that tells us the total work done. Okay, so then from there we know that the total work done per unit time okay, is really dw over dt. Okay, is really the amount of work done per unit time. This is really, as we said, this is equivalent to the voltage Okay, so this is really voltage times the current. Okay, so this one will really give us Li di over dt. Okay, so now let us assume we have I originally is 0, and we turn on the switch, and the current increased to I. Okay, so then we just count the amount of work, okay, done. It's really dw over dt over time. Okay, so that is really just this integral here. Okay, so this is really Li di. Okay, so this tells us is really 1/2 Li square. Okay, and you can see from here that the amount of work only depends on the self-inductance, which is fixed once you have your circuit fixed. Okay, and then it depends the final the current that we have, and it doesn't really depend on how long we take to crank up the current. Okay, it only depends on the final value of the current. Okay, so this is how we do it. Okay, calculate the energy that are stored in the magnetic field. However, we can, here is this case we are talking about. We are talking about the line charge. Okay. Okay, because we are talking about a while. Okay, so we can make it more general so that we can easily also write down the work, for the surface current and also for the volume current. Okay, the way to do that is, we can use this trick. As I said, the magnetic current, the magnetic flux through this loop is really this L times I. And this magnetic flux, of course, can be written as B dot A. Okay, so this is really the definition of the magnetic flux. Okay, and now we can really, B is really del cross A dot dA. Okay, and then we really can use the Stokes theorem, and we convert from the surface integral to the line integral. So it really becomes A dot dL. Okay. Okay, so this is what we have. Okay, so in other words, that Li is really equals to this integral. So now is really, Li is really this. So I put one I outside. So we have really A dot dL here. Okay. So what we can do, because really we can do I dL. Okay, we can do I dL, and because the current, as we said, is really along this dl direction, so we can also write down this as A dot I. Okay, which is really the current direction. Okay, then we multiply by dl. Okay, I mean, as I said, the I direction is really parallel to the dl direction. Okay, so we just move this direction to this I. Okay, we integrate over dl. Okay, so this is the equation that is equivalent to this. Okay, it looks more complicated. Okay, but the reason we wanted to do this is we can easily extend this for the surface current and the volume current. Here, of course, is for the line current. Okay. Now, if it's a volume current, okay, we just replace this J, this I with J with the volume current. Okay, we integrate over all the volume. Okay, so if it's a surface current, okay, okay, we can also just write it down as sigma. Okay, A dot This is sigma. This is surface current times the area. Let us say call it dA. Okay. So this is just to make it easier to extend this formula, for surface and also for the volume currents. Okay. We can also do even better. Okay. And we can really write down this work entirely in terms of the magnetic field. Okay. So the way to do this, let us look at this, the volume current. Okay. So we have W is really the A dot J d tau. Okay. Okay. And we know that J is really we from Ampere's law, we really know that mu 0 J is really equals to del cross B. Okay, so this is Ampere's law. So what we do is we just plug in. Okay, so we have mu 0, we move it out. Okay, and we have, then we have this integral A dot del cross B d tau. Okay. Okay. Now we needed to do this integration by PHYS. Okay. So what do we have? We have to use the formula that we learned from this vector analysis. So what do we have is really, if we have a divergence of a cross product, it will becomes this. Okay. The reason is, we wanted, we have this term. Okay. So in other words, that this term is really becomes B dot del cross A minus del dot A cross B. Okay. So this is what we have. Okay. So once we have this, we can just plug in. We plug this into this equation. So 2 mu 0. Okay, so we have from here, here we can remember del cross A is really B. Okay, so B dot B give us B squared. Okay, minus del A cross B. Okay, so this is what we have. So after that, we have B squared d tau minus del minus this del dot A cross B d tau. Okay. And now we have two terms. Okay, so let us write down the first term. Okay, just write down B squared d tau. The second term, we can also convert this volume integral to the surface integral. Okay, so so this is will be, you can treat it as a one vector. Okay, to the surface area. Okay, so this is what we have. Okay, so this is the surface. This S is really the surface bounding this volume. Okay. Okay, so this is what we have. Okay, so now let us consider that we can take the volume. Okay, we can integral. Okay, we can take the entire volume that are occupied by the current. Okay, so let us say this is the volume. Okay, so and this is the surface that are bounding this volume V. Okay, but we of course we can integrate over this entire volume that are occupied by the current. Okay, no problem. We can do this volume integral and do this surface integral. Okay, but if we can extend the region and let it to be larger than just the volume occupied by the current. Okay, because that's okay, because the current J is zero out there anyway. Okay, so you can see that if we make the region larger, and we will have larger contribution, of course, to this volume integral. Okay, and then of course this surface integral will become smaller, because if we make the volume bigger, then the surface gets further from the current, and then this A and B, they both decrease. Okay, so now you can imagine that if we integrate over all space, okay, then this surface integral goes to 0. And if this goes to 0, we can have the amount of work is really, this is integrated over all space. Okay, so this is B squared d tau. Okay, because if we integrate over all space, then this surface integral, okay, will become 0. Okay, and you can see that we can view this b0 b squared divided by 2 mu 0 can be thinking about this energy density. Okay, and this can be treated as the energy stored in the magnetic field. Okay, and you may find that it is strange that it takes energy to set up a magnetic field. Because we already discussed before that magnetic fields themselves do no work. Okay, so then why we still need to take energy to set up a magnetic field? So the main reason is that in order to produce a magnetic field, originally there was none. Okay, so that means it requires us to change the field, to go from 0 to some value of B that is non-zero. So a changing magnetic field, according to Faraday, induces an electric field. And we know that the electric field, can do the work. So in other words, that, when at the very beginning there is no magnetic field, and there is no electric field. And also at the end, the magnetic field becomes stable, doesn't change. There is also no electric field induced. However, in between, where the B value goes from 0 to some non-zero values, the B field is building up, and there is an electric field. And it is against, this that the work is done. Okay, so that is what we had before. That is the reason why there is magnetic field. There is a work that we needed to do in order to set up the magnetic field. Okay, so remember that when we talk about electrostatics, we talk about the electrical energy, that are stored, and we said, the equation is really half epsilon 0 E squared d tau. Okay, and with a density that is epsilon 0 times E squared divided by 2. And here you can see that the magnetic field, the energy stored there is really just 1 over 2 mu 0, and then B0 d tau. Okay, and with a density that is B squared divided by 2 mu 0. So you can see that they are very similar to each other. Okay, and also you can see that why we didn't discuss about the amount of work done by the amount of energy stored in magnetic field before. When we talk about the statics. We didn't discuss about that, but we discussed that the amount of energy stored for this electrostatic case. So the main reason that you see that the amount of work is really due to during the process that we build up this magnetic field. It's really the induced electric field, okay, that does the work. Okay, so that is why we only discuss about that, when we talk about varying electric field and also magnetic field. Okay. So now I just wanted to talk about one example. Okay. So let us assume there is a long coaxial cable. Okay. So we have this long coaxial cable. So we have another cable that is between. Okay. So this is a long coaxial cable. Okay. And one has a radius of R, A, and then the other one has a radius of B. Okay, so there is a current that are flowing on the inner surface of the cylinder, and also the current goes back on the outer surface of the cylinder. Okay, so that is what we have. And we wanted to find out the magnetic field stored, in these some sections, with a length of L, let us say. Okay. And in order to find the energy, what we really is really this integral, the formula that are showing here. Okay. So what we really needed to do is really to find out the magnetic field. Okay. The way to do that, of course, is we can define Ampere loop, okay, and we can use the Ampere's law, and we can find the field. Okay, so this is really, is really B dot dl equals to mu 0 times I, the current that are included inside this. Okay, so this is B really divided 2 pi s. Okay, let us say its distance is s, really equals to mu 0 I, the current. Okay, so we have B is really mu 0 I divided by 2 pi s. Okay, and we know the current is really along the phi direction. Okay, so that is what we have. Okay, so once we have B field, and we can really have the energy density is B squared divided to mu 0, and which give us is mu 0 I squared divided by 8 pi square s square. Okay, so this is the energy density, and then the amount of work is really just this density times d tau. Okay, the volume. Okay, so this is mu 0 I squared divided by pi square s square. So this d tau, we can consider a very small volume change at the ds here. Okay, so this volume change is really the length is 2 pi times s. Okay, then of course times ds. Okay, so this give us the surface here. Okay, and of course we needed to times we are talking about sorry, I should really cover this whole whole length. Okay, times L. Okay, because this is the volume. Okay, there are three. This is this length times this small change of the distance change, and then times the length of this axial cable. Okay, so if you add together, we really have, if you do the integral, mu 0 I square L divided by 4 pi log B divided by A. Okay, so this is about the the amount of energy that are stored, in this this cable with a length of L. Okay, and from here we can also calculate the self-inductance, because W is really equals to 1/2 Li square. Okay, so from here we can calculate the inductance is really mu 0 times L divided by 4 pi log B divided by A. Okay, so this is this method to calculate self-inductance is also very useful. Okay, so this is for example, just to show you how we can use it to calculate the amount of energy that are stored in the magnetic field. Okay. So now, after we do this, okay, so this is a very important equation. So this is really called Maxwell's equation, okay, which is the most important equations for the classical electrodynamics. Okay, so the electrodynamics before Maxwell. Okay, at that time, we just summarize all the equations that we have learned so far. Okay, we have this is called Gauss's law. Okay, so del dot E equals to rho divided by epsilon 0. Okay, so we also have del dot B equals to 0. So there are no name for this. I mean, we really see that there are really no magnetic charge. Okay, then we talk about to have Faraday's law. Okay, minus partial B over partial T. Okay, this is really Faraday's law. It's really the changing magnetic field, will cause the change, will create an induced electric field. Okay, and then we also have del cross B equals to mu 0 J, which is Ampere's law. Okay, so these are the equations, that we have, that Maxwell, before Maxwell. Okay, this is all the knowledges that people have, okay, at that time. So however, there are some problems, with these four equations. They are really not consistent with each other. Okay, so the reason is really this. We know that for any of a vector A, let us say, the divergence of core is always 0. Okay, so this is, we proved that before. Okay, so now let us look at these two equations. Okay, one is Faraday's law, one is Ampere's law. So we look at this. Okay, so we first look at this, which is their, if we calculate the divergence. Okay, so what we have is really del dot minus partial B over partial T, which is minus partial T del dot B. Okay, and we have, from here, we have del dot B is equals to 0. So this is consistent. Okay, so these two equations, okay, really already indicate del dot del cross E should be 0, and it is 0. So this one is fine. However, when we look at this Ampere's law, okay, so we have this. Okay, so then what we have is, because it is this, so mu 0 del dot J. Okay, so we have this. Okay, and we said this one should be equals to 0. This is really from vector analysis. Okay, the divergence of any, the core of any vector should be equals to 0. but this one may not really equals to 0. Okay, really depends on the current that we have. So in other words, that there are some inconsistency, okay, in the four equations, around that time. Okay. So this one you can also see from the example here. Let us look at there are some battery, for example, that will charge the two. This is a parallel plate capacitor. Okay. So we have the current that are going on, and then we have the charges that will show up in this this capacitor. Okay. So now what we do is we wanted to just check this Ampere's law. Okay, because there are some problems with this Ampere's law. So if we define it as a surface like this, okay, just here, around this loop, okay. So, in principle, if we do the integral, okay, remember that if we do the surface integral, okay, so it's really b dot dA. In principle, it should be really equals to the I of the current that I included, okay, on that surface, okay. So now if you see that if we choose this surface, okay, and you can see that the current that I included is really equals to the current through the wire, which is I, okay. However, if we take a bubble shape, this surface, and this bubble shaped surface, passes, between the capacitor plates, okay, and we know that there are really no current that are flowing through, okay. So the actual enclosed current is really 0, okay. So that caused some problems, okay. So Maxwell, knows this problem, okay, and he, thought about this, and really, add some modifications, for this Ampere's law, okay. So we will talk about Maxwell's modification for Ampere's law. Okay. So what we want is really, I said, this is the problem. Okay. So the Ampere's law has a problem. Okay. So what we can start is we can first look at the continuity equation that we described before. Okay. So what we had before is really del dot J plus partial rho over partial T, okay, equals to 0. You can go back and look at how we derived this equation. Okay. So this is what we have. Okay. And we said there are problems with del dot J. Okay. So we can look at this del dot J. Okay. What we have is really partial rho over partial T. Okay. And because rho is really, you can see from here, rho is really epsilon 0 times del dot E. Okay, so this is really epsilon 0 del dot E. Okay, so this is what we have. Okay, so we can move this del out because this is the derivative with respect to space coordinates, and this is with respect to time, so we can really change the order. Okay, so this is what we have. Okay, from here you can see that this is del dot J, this is del dot other things, so we can really write it down as J plus epsilon partial E over partial T equals to 0. Okay, So this is really, this is still the continuity equation, okay, because we derived it from there, okay. So you can see that currently we have a problem with this Ampere's law, okay. So this side should be 0, okay, but this side turned out to be not 0, okay. And we have this equation, okay, really says this is equals to 0. So then just Maxwell had the idea, can we replace this del dot J, with this, okay. And I think that is his smartest idea, okay. So now once you replace this J, okay, with J with this, so we can have Ampere's law. Ampere's law now originally is mu 0 just J. Now we just replace this J with this, okay, with this. Now you can see that if we do del dot del cross B, and we know from vector analysis, we know this should be 0. And from here you see that this is really del dot this J plus epsilon 0 partial E over partial T, okay. Because of the continuity equation, this one is also 0, okay. So you can see that from here, everything becomes consistent, okay. And so this is the equation is really called Ampere's law, but Ampere's law with Maxwell corrections, I think. So this is Ampere's law and with Maxwell's corrections, okay. And you can see that this one, you can see the unit, this is current, so this one must also have a unit of current, okay. So this is sometimes we use this JD to indicate that it's really partial E over partial T. So this is sometimes called displacement current, or some people call it Maxwell's displacement current, okay. So this is what we have, okay. So now the Maxwell's equation now becomes this rho divided by epsilon 0 del dot B equals to 0, del cross E equals to minus partial B over partial T, del cross B is really mu 0 J plus mu 0 epsilon 0 partial E over partial T, okay. So these are really the famous Maxwell's equations. These are of course one of the most important equations in the history of physics, okay. And from here you can see that if E is a constant, okay, and of course partial E over partial T will becomes 0, and we go back to the Ampere's law, okay, that we have for this magnetostatics, okay. And also that even when E is changing, okay, because you may remember that epsilon is a small value, so this term this displacement current is usually much smaller than this J, okay. And that is why Faraday didn't really detect this during his experiments. However, you will see that this term is really important when we talk about the propagations of electromagnetic waves, okay. And also you may see from here, this JD is called displacement current. It's not really a real current, in the sense of a flow of real charges. When we talk about a current, we always say it is a flow of real charges. Okay, it is only this term has the dimension of current density, that is added to the euro current that we talked about here, J, that is used in Ampere's law. Okay. However, let us say if J is 0 and E is non-zero, okay, and E is changing, and we found that it really indicated that a changing electrical field, okay, when E is changing, it induces a magnetic field. Okay, so this is really very important. A changing electrical field induces a magnetic field. Okay, so this is what we learned from this equation. And from here, we already described before, a changing magnetic field, okay, induces an electric field. So you can see that these two equations really indicate these very, very important factors, okay, about the electrical field and magnetic field. A changing electric field induces a magnetic field, and a changing magnetic field induces an electric field. Okay, and we will talk more about the indications. What are the results of these Maxwell equations? In chapter 9, where we spend a lot of time talking about the propagations of electromagnetic waves. Okay, there are a lot of things we will talk about, and these are really, the entire theoretical content of classical electrodynamics. All these equations really are important, for the behaviors of this electrodynamics. Okay, we will talk more